So really delighted to have the opportunity to talk to you today about our package together with my colleague and friend, Ezra Morrison, who is going to jump in and talk about the stats in a few moments. Okay, so our goal was to build a reproducible and easy package for translating quantitative antibody responses measured in population samples into meaningful measures of infection burden in the population, like incidence rates. So here we're reorienting from looking at stool shedding, pathogen shedding, to thinking about antibody responses measured in people in blood or serum. So a bit of a different perspective here from the other talks. Oh, this is an old version of the presentation. Okay, so then specifically, we are interested in grappling with some really important challenges that we face when looking at serologic markers. And one of those is that we know that antibodies decay. So we know that, just like we were talking about shedding, we know that antibodies decay in the blood, and often that's not well characterized. So you have an exposure to a pathogen and you mount an IgM or an IgG response, and that fades over time, and it fades at different rates depending on a lot of factors. There's a lot of heterogeneity. So it could be age, it could be prior exposures, it could be immune function, right? So that was a really key metric for us to grapple with here. And also we wanted to consider that we know that there's measurement error in antibody responses. We know that when you measure the same response in the exact same antibody levels in two different wells of an ELISA plate, that you won't get exactly the same measurement. So that's important to grapple with. And also that, my slides are gone. Also that you have, what was it? Cross-reactivity, there it is. Sorry. That you can have an exposure to an antigen and then have an exposure to another antigen, but still mount a response if there's some relation there, if there's some cross-reactivity. Sorry, these are an old version. So the origin of our interest in this topic came from a project that was funded by the Bill and Melinda Gates Foundation to build a tool that could characterize the burden of typhoid in populations. And we know that typhoid faces a lot of surveillance challenges because the number of clinical blood culture confirmed cases is just a fraction of the true infection burden because of low sensitivity of blood culture and challenges with grappling with care-seeking behavior where individuals seek care at surveillance sites, et cetera. So we sought to build a serosurveillance tool for typhoid, and from that then built our package that can now be applied to many different pathogens. And the reason that just taking one step back, this was so important for typhoid in particular is because there are safe and effective vaccines available for typhoid, but the big gap is that countries don't have the data they need to inform where and among whom to prioritize vaccine rollout. So that's where this kind of method and package fit in terms of the public health data needs. And I just have to also give a shout out to a mentor and friend, Peter Tunis, and you've seen a bit of his work come up in the other sessions that maybe is the underlying theme under our presentation. So he's a biostatistician who originally came up with the concept, him and his colleagues, of combining within host models of antibody decay together with cross-sectional population antibody responses to generate seroincidence estimates from cross-sectional data. So we are pairing together cross-sectional population serosurveys. So imagine this is a serosurvey that we conduct, and the color here of the individuals represents their quantitative antibody response, going from blue to dark red at the highest. So that's one component. Then the other component is that we build these within host models of antibody dynamics. And theoretically, that this piece just has to be done one time for a pathogen for a specific biomarker, whereas you would conduct many different cross-sectional serosurveys. So just to illustrate how we're doing this is real data, actually a subset of real data of blood culture confirmed typhoid cases that we followed over time in our study. We followed actually 1,420 individuals, and this is just a subset of 100. And so each dot is a sampled response that we measured, and the lines are connecting individuals there. So we follow them over time. We visit them in their household, and they generously give blood samples so that we can characterize these dynamics here. We then fit a within-host model to this data, which Ezra is going to describe more of the math. And we use the antibody dynamics now to actually take quantitative responses in the population and characterize time since infection, which allows us to calculate the incidence rate. I'm going to hand it over now to Ezra.
Okay, hopefully everyone here knows what incidence is, but just to make sure, it's the rate of new infections in a population per person time at risk. You can also think about it from an individual's perspective as the probability of becoming infected, given that you're at risk of becoming infected at a given point in time. So the probability density. So that is a hazard function in survival analysis. And that is useful because it allows us to set up a pretty simple model. Let's start with the data that we've got. We're doing a cross-sectional survey. So we recruit some people from a population. We measure their antibody levels, which we'll call Y. And then each person was most recently infected at some point prior to the survey, or maybe they've never been infected. And we'll call the time when they were most recently infected T, or the time since they've most recently been infected. We don't know T. It's a latent variable. And that's too bad, because if we did know T, then we could use a simple model to estimate incidence. We would assume that the incidence is constant and homogeneous across the population and over time. If homogeneity is not reasonable, you can always stratify or subset your population until it seems like a reasonable assumption. And we also have to assume that people are always at risk for a new infection, even if they've just been infected. For a disease like typhoid, that may or may not be possible, but it's an area we're actively working on adjusting for. So if you have this constant and homogeneous incidence and no lasting immunity, you can set up an exponential distribution model. Nice and simple. The probability that you've been infected T units ago is the probability that you haven't been reinfected since that time. So you have the incidence rate at time T, which is lambda, and then your survival function from then until the survey happens. This would be great because then we could, like I said before, the individual hazard parameter is the same as the incidence parameter for the population. So we can estimate lambda using standard maximum likelihood techniques. You take the derivative of the log likelihood, you set it equal to 0, and you solve, and you end up with 1 over x bar. 1 over t bar is your maximum likelihood estimate. Too bad we don't have t. Instead, we just have y. So if we want to relate the data we have to the parameter we're interested in, which is the incidence rate, lambda, you need to express that distribution in terms of lambda. So we express the distribution of y as a convolution over the joint distribution of y, your biomarkers, and t, the time since infection. And then you can decompose that joint distribution into a conditional and a marginal. And here, do I have a laser pointer? Here we go. Oops. Laser pointer moves the slides. Too bad. Here is that distribution that involves lambda. This is a nuisance distribution, which gets us back to the picture that Kristen just showed you. Here is that nuisance distribution of how the antibodies change over time after infection. So if we can estimate this model, we can plug it in to our joint distribution, and we can still, with a little bit more complicated math, get the maximum likelihood estimate. So we've reduced our problem from estimating incidence to modeling how antibodies change over time after infection. And this model, we also have a relatively simple model. We start with a lock of Altera predator-prey model. So the predator is the antibodies and the prey is the antigen, the pathogen. And we simplify it because it's a little bit hard to estimate all the parameters, and we think we can remove some. But basically, the pathogen is growing, but it's being inactivated by the antibodies, and then the antibodies are growing exponentially. Once the antibodies have eliminated the pathogen, then you have a not quite exponential decay, but a power function decay, which allows us to have the possibility that you might retain antibodies for a long period of time, or you might not. If you want to play with the parameters of this model, we have a Shiny app that you can go to and move all the sliders and see how that model works. And now I'm going to pass it back to Kristen to talk about the other pieces of our work.
Thanks, Ezra.
Yep.
That was great. I'm going to grab that. Okay, so we've wrapped this all now into an R package, which is called Sero Calculator, and that is on CRAN now. So you can download it, or you can check out our GitHub and download the development version. And I do have to just acknowledge that this is a complete team effort, and we have a team of software developers based out of Nairobi, here with Chris Orwa and Sky High Technologies, and also our graduate student, Christina Lai, here, who's just been a really integral component of all this work. So you can check out the package. There's really simple, we hope, functions to load in the antibody decay models. And those we have examples hosted on Open Science Framework. We have implemented auto plots that automatically plot these different objects, such as the antibody decay dynamics. And then you can load in your own cross-sectional population data or practice loading data from Open Science Framework to see how it works. And then all that is wrapped into a really simple function called estincidence or estincidence by, which give you overall incidence estimates or stratified incidence estimates. So here, this is using data that we published in Lancet on the incidence of enteric fever in the 3 different SEAS sites. We also have a Shiny app for Sero Calculator for those that are not comfortable with our programming, where you can simply upload and point and click through these different functions. We've been using, combining these new serologic markers together with our package. I don't know what happened with the formatting here, but together with the R package to fill in some of these data gaps, especially for enteric fever. So we've been partnering with many different organizations across Sub-Saharan Africa, South Asia, Southeast Asia, and South America to generate data to fill in these gaps and help inform typhoid conjugate vaccine rollout. We've also applied this tool to estimating the seroincidence of scrub typhus, and that's been published recently in American Journal of Tropical Medicine and Hygiene. We also have a vignette on that, and we're working on expanding to cholera and Shigella now as well. And finally, I have to end with our most important slide, which is to acknowledge that this is all a work of a teamwork of many different collaborators around the world, and would not be possible without our study participants, of course, and we have to gratefully acknowledge the funders, the NIH for the R package, and then, of course, the Bill and Melinda Gates Foundation for all the typhoid work. Thanks for your attention.